Hi everyone, and welcome to our sessions for today, which called Infra as Code Stop Clicking and Start Declaring. The tagline says it all. Your console clicks are technical debt, where by end of this session you will understand exactly what does that mean. And you'll have seen a full production infrastructure deployment with zero manual steps. In our session for today, we're going to cover the philosophy, walk through a 5-stage automated pipeline, and then I'm going to do some kind of a live demonstration, real commands, real AWS, and real results. Let's go. What does a quick console click really cost? Before we talk about this solution, let's talk about the problem itself. And I want to be specific because manual processes are bad. They are too vague to care about. Like, let's say in average, 47 clicks, that's what it takes to deploy a basic 3-tier application in AWS console if you know exactly what you are doing. That means 47 clicks, 47 decisions made by a human in sequence, and none of them are documented. Zero audit log. When something breaks at 2 a.m. and you need to know who changed that security group, there is nothing lead you to any evidence. No record, no name, and no timestamp. 3 times longer to reproduce bugs between environments because staging and production were both configured by hand and subtly different in ways nobody remembers. And as we can say, an infinite drift, a configuration drift every time someone modifies or clicks something. Every time someone touches the console, the gap between what the code says and what AWS actually has grows a little wider until one day it bites you in production. These are not edge cases, these are Tuesdays. Let me give you 4 stories. I'm not going to tell you which clients these are from. Starting with the first one, the 3 a.m. security group. Well, production is down. After an hour of investigation, someone finds a security group that was open to the public, wide to the public. Port 22, full SSH access, 6 months ago. No ticket, no comment, and the engineer who did it has left the company already. So in this case, we have no audit trail to revise. Nobody knows if it was intentional. Nobody knows who did what and when. Going to the forgotten NAT gateway use case, where a $4,200 monthly bill spike traced to a NAT gateway that was created for a demo, and someone was going to delete it, but it's obviously has been forgotten. The budget alarm has caught it, and the dev had left 2 weeks earlier. Staging is not production and does not equal each other's. QA sign off, the release goes live, production burns. It turns out that the RDS instance was different between environments. We are talking here about configuration differentials. Both were set by hand, both were close enough, but in fact they were not. Moving to the bust factor, where one senior DevOps engineer leaves, with him goes the knowledge of how the VPC peering was configured. 3 engineers spent 2 weeks reverse engineering it. That's 6 weeks of engineer time to redocument something that should have been coded from day one. Every one of these had the same root cause: infrastructure that lives in someone's head or someone's clicks instead of code base within a version control environment. So what's the alternative? Of course, infrastructure as code, And the keyword here is not code. It's all about being declarative. On the left side, we can see ClickOps, where we tell AWS or whatever the cloud provider is what to do step by step. Log in here, set this, repeat for staging, repeat for production, and hope that nothing drifts. The problem here is that each of those steps in this process are ephemeral. The moment you close the browser, the knowledge is gone. Meanwhile, on the right hand, you declare using infrastructure as code what you want to exist, not how to create it, what should exist. So in this case, this infrastructure as code provider, which is Terraform, it figures out what's currently in AWS after reading the declaration of ours and calculates the difference and makes it so. Look at this code block, for example. It reads almost like English. There should be an EC2 instance. Its AMI comes from a variable. Its instance type comes from a variable. It belongs in the subnet. It has 3 tags or blah 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 here. And this file goes into Git. It gets reviewed in a pull request and the commit history. This is documentation. If it's not in code, it should not exist in production. That's the rule. Terraform 101. 4 concepts, that's all you need for the rest of the session. Starting with provider. Provider is the plugin that knows how to talk to a cloud API. For us, it's AWS. You declare which provider you are using and how to authenticate in one block within your config. Number 2 is the resource, a single infrastructure object like an EC2 instance, an S3 bucket, a security group. They are all single resources. You declare each one and Terraform manage its entire lifecycle, including creation, update, and destruction. Number 3 is the state. The state is Terraform's memory. It records what has been created, where it is, and what its current properties are. We store the state remotely in an S3 bucket, usually with a DynamoDB log, so multiple people can work without overwriting each other. Without state, Terraform would not know what to change versus what to create from scratch. Moving eventually to the plan and apply. The Terraform plan show you a difference in fact between the last stable state of the infrastructure and the changes that are gonna be made. Exactly what we will be create, what will be changed, and what will be destroyed. Before anything happens, Terraform apply executes it. So you never run apply without seeing the plan first, no surprises, and that is Terraform. 4 concepts, everything is just writing HCL. Now here's where it gets interesting. Terraform on its own, it's powerful, but Terraform inside a pipeline is transformative. In this case, we have built a 5-stage pipeline that runs on every single pull request. Let me walk you through it. Starting from stage 1, format and validate. The moment a PR is opened, we check that the code is formatted correctly and the syntax is valid. This runs in a seconds with 0 cloud cost, where it catches typos and formatting issues before a human reviewer ever looks at it. Moving to stage 2 with the security scans, where we run Trivy and Checkov against the Terraform code. Without deploying anything, they catch misconfigurations like open S3 buckets, unencrypted databases, overly permissive IAM policies or security groups before they apply. Then we have the cost estimation step, where Infracost calculates the monthly cost of every resource in the PR and posts it as a comment, so the reviewer knows the dollar impact before they approve. So you have like an overall visibility over the changes, like if I pumped up the EC2 instance size, how much it will be costing more. Moving to the plan and review, the Terraform plan runs against real AWS infrastructure and the output is posted as a PR comment. The reviewer sees exactly what resources will change, and then finally we have the apply. So when the PR merges to a main branch, apply runs automatically, and every night a scheduled job runs plan against live infrastructure to detect any manual changes. If something changed outside the pipeline, then we will know as an output of that scheduled job within 24 hours. All of this runs on our self-hosted GitHub Actions runner. In fact, nobody's runs Terraform locally. Nobody's has deploy keys on their laptop. So we ensure the security of infrastructure access only from the GitHub Actions and GitHub repository. Now, getting deeper in stage 1, format and validate. Stage 1 run 3 commands. Terraform FMT checks formatting. Terraform init with the backend false downloads the providers without touching the state backend. Terraform validates checks the HCL syntax and provider schema. Why does this matter? Because the alternative is a code review where half the comments are about indentation and missing brackets. Those conversations have no business happening between humans. Let the machine cat them. This stage runs in under 30 seconds, it costs nothing, and it means that by the time a human reviewer looks at the PR, they are only looking at logic, not style. Stage 2, which is security scanning. I want to be transparent here about something. We originally planned to use a tool called DFSec for the stage, but this tool was archived and deprecated recently and replaced with Trivy, which is a broader and more capable scanner. We updated the pipeline accordingly. Trivy scans the Terraform code for misconfigurations, not the running infrastructure, the code itself. It finds issues like an S3 bucket missing, public access plugs, a security group with public access on port 22, for example, before they apply. That's the whole point. And we have the other tool, which is Checkov, which adds a second layer within over 1,000 policy checks. It maps every finding to a compliance framework. We are referring here, for like example, the CIS benchmarks, the ISO controls, the SOC2 requirements. So the security teams get findings in the language they speak. The results from both tools get posted as PR comments here and uploaded to the GitHub security tab as SARIF reports. Every findings has a line number, a severity, and a remediation suggestion. Think about what this replaces. A manual security review that happens at the end of release cycle when fixing something costs 10 times more than fixing it here. At stage 3, we are talking here about cost estimation. Every PR showed its dollar impact before anything is deployed. How is that possible? Well, we are using here an external tool called Infracost. Infracost compares the PR branch against the base branch and calculates the difference in monthly AWS spend. It posts a table directly in the PR. Like this change adds an RDS instance, let's say 50 buckets, $50 per month. This change upgrades the instance type from T3 medium to T3 large. Let's talk about $20 per month. So the total estimated change will be like some kind of $70, let's say, or like X dollars per month. So in this case, the reviewer can see this before they approve, The finance team can see this before the change ships, and there are no more end-of-month surprises, especially where someone discovers a forgotten resource that has been running for certain weeks or couple of weeks. Infracost is free tool, in fact, to use in our case, where we are using an API key linked to the free account we have already signed up to pull up AWS pricing data from the AWS account with no usage limits within the pipeline. Now jumping to the stage 4 where we have the plan and peer review. The plan comment turns infrastructure changes into something reviewable by anyone. So this is the output you just saw on the previous slide in the demo preview. Terraform runs plans against real AWS, and the full output, every resource that will be added, changed, or destroyed, get posted as a collapsible comment on the PR. Here's why this matters. A developer reviewing a Terraform PR might not know what every resource type does, but they can read 2 resources will change, 0 will be destroyed, and ask the right questions. They are not flying blind. The plan also is saved as a workflow artifact with a 30 days retention window. That's your compliance trail. Every change has before and after snapshot tied to a commit, tied to a PR, tied to an approver. And we use also OIDC authentication between GitHub and AWS. So GitHub Actions proves its identity to AWS cryptographically. There are no AWS access keys stored anywhere as secrets. The credentials are temporary and expires when the job finished. Now to the final stage where we have 2 parts mainly. The first part is auto apply. Auto apply. Now moving to the final stage, which is the apply and drift. Here we have 2 parts. In fact, we have the first, which is auto apply. When a pull request merge to main, the pipeline runs Terraform apply automatically. No manual step, no one SSHing into server, no one running a command locally. The pipeline is the deployment mechanism, full stop. And the second is drift detection. Drift detection here, every night at 2 a.m., a scheduled workflow runs the Terraform plan against live AWS infrastructure. If the output shows any changes, let's say someone clicked in the console, AWS automatically modified a setting, the pipeline opens a GitHub issue and sends a Slack message or a Slack alert, or it depends on how we configure the trigger. This is how we enforce the rule that the console is read-only. You can't physically stop someone from clicking in AWS, but you can detect it within certain amount of hours and surface it to the team. Now, let's talk business value. Let me bring this back to business outcomes. What we gain in the day we start following infrastructure as code and implementing in our projects, 10 times faster environment setup. A new staging environment, full resources like VPC, EC2s, RDS, takes about a couple of minutes with Terraform apply. By hand in the console, assuming you know exactly what you're doing, you need like an average of 30 minutes minimum, and that's if nothing goes wrong. 100% infrastructure audit trail. Your Git history is your changelog. Every modification to infrastructure is a commit with an order, a timestamp, and a PR with approvals. That's not just useful, that's what ISO standards and GDPR auditors ask for. Also, we have a 0 manual deploy steps. The only path to production is the pipeline. This eliminates an entire category of human error range. And of course, we have 2 times faster disaster recovery. where your runbook is not a Word document anymore. It's a Terraform apply, a Terraform code base. If a region goes down, you run the same code in a different region, and that's your DR plan. Now, let's go to a live demonstration of what we just explained. Let's start with our GitHub Actions workflows. Let's start with the Terraform CI workflow, which will be triggered on pull request to branch main. Of course, we have set some permissions for the workflow, and we have here the environment variables for the jobs inside. So starting with the format and validate, the first step, we are formatting check the Terraform code to avoid any typos or misspells, and then we are validating the configuration, and then post the format result to pull request. After that, we are going for security scanning, where we are using the actions for Trivy and also Checkov at the next step. Also, we can here we can select some security checks to be checked, or we can stay on we can leave it empty so it check against the default security checks. Both of these will run and continue on error, just in our case because we are testing some kind of a demo. It's not recommended for production environments to continue on error for these, because you don't need some security issues on your code and your infra on your production environment. So after that, we are going for cost estimation, where we are using Infracost actions for estimating costs. Of course, we are passing here the infra or the Infracost API key, which we have stored in GitHub secrets for you to be used within the GitHub Actions workflow without being exposed to the public. So we are generating, first of all, a cost baseline based on the main branch. Then we are generating a difference between the main branch and the PR branch to make the difference clear in cost. If in our case here, we have the same resources in the main branch, and in our branch we are working on future update branch, just for demonstration purposes. So we will add some extra resources right after we finish with the workflow, and check how the difference will be printed to the PR. Then we are hitting Terraform plan, which of course is authorizing and authenticating with AWS using OIDC, where we have already set up an identity provider and the NIAM role with access to the infrastructure, and specified a custom trust policy to trust only this Terraform repo, this GitHub repo in our GitHub organization. So we are passing here the ARN of that role, with here containing the role name and the account ID stored in GitHub secrets, alongside with the AWS region. Then we are hitting the Terraform setup, the Terraform initialization for the directory, and then running Terraform plan, which will print an output of the planned changes and the resources to be created, destroyed, or even changed. Then we are posting the plan to the pull request. So for now, we're gonna test that CI workflow by, first of all, we are working on the feature update branch, which has the exact same code from main branch. And it's good to note that there is no current infrastructure provisioned on the AWS account. So let's try to duplicate this load balancer application, for example, and change the name for ALB2. It will be an application. Also, we're gonna change this name, the resource name. Okay, subnets, the security groups, and so on. Okay, so this new resource should be an addition to the existing resources defined in the main branch, not in the AWS account, but in the main branch. So let's commit and push to the feature branch and see what will happen. Okay, so let's say here duplicate ALB, and let's push to update. And let's check the pull request. Okay, we have already opened a pull request from the update branch to the main branch. We can see the demo pull request here. So let's check the latest updates. Okay, starting from our commit here, from duplicate ALP, we have the stage 1 format and validate success for both FMT and the Terraform validate. We have the Infracost report. We can see here that there is some recommendations from Infracost that we can do to optimize our infra regarding to be like more visible in terms of cost management. We can see here that there is a monthly estimate increment. This one was because of the load balancer we have duplicated. Then after that we have the security checks here for both Trivy scan and for Checkov scan. We can here see that Checkov has some failures. This is due to some security requirements we have already skipped due to demonstration purposes, and here we can see the plan stage. We can see here that Terraform has used the selected provider to generate the execution plan. We can see here that an autoscaling group named app that will be created within the alongside the following attributes. Each resource will be planned here with all its attributes. So once we have the plan ready, we can merge the branches into main. Then we can go back to the apply workflow. The apply workflow, in fact, it runs on push to main, where once the merge request is or once the pull request is closed and the branches are merged, then this workflow will be triggered. It's pretty the same as the Terraform CI workflow, but it only contains the Terraform apply. We are authenticating and authorizing with the AWS account using OIDC. Then we are initializing the Terraform directory. Then we are applying the planned infrastructure changes with the sensitive variables we defined already in GitHub secrets. Then we are capturing the outputs and saving the outputs as an artifact in GitHub. So let's get back and merge the pull request. Let's confirm the merge. And we can see that the pull request has successfully merged and closed. So if we go to the Actions tab, we can see that a new workflow has been triggered on branch main that will handle the apply process of the planned infrastructure. We can see here the initialization of the Terraform directory and then the output of the apply command. In fact, Terraform apply might take some time depending on the resources we are provisioning. We can see here that some resources are being created. We can see here the creation complete after some period of time, and so on. So this is gonna take some time, especially on the RDS instance. So we're gonna be having a look back once the apply is completed. And finally, the DB instance has been provisioned and the apply stage has been completed. We can see here that the apply complete. Here's the resources, the new resources that have been added after we ran the apply step for a second time after some resources has been already applied, but like we faced some issues and fixed them, then only one resource that was left, and now it's up, which is the AWS database instance, the RDS instance. We can see here the outputs values including the load balancer DNS name, the zone ID of the load balancer, the autoscaling group name, the subnets of the database, the private subnets and the public ones, the S3 bucket ARN, and so on. So until here, we have our infrastructure up on AWS. We can check these are the new load balancers we have provisioned, we have declared within our code. This is the autoscaling group we have also declared. We can see here the instance management. We have a couple of instances. They are appearing as unhealthy due to some internal errors, and that uh, that situation in fact comes from the health checks, since they are attached to a load balancer, an application load balancer. It do some health checks periodically. So if the health check is failed, then the instance is marked as unhealthy. Also, we have here the database, the RDS instance, which is Postgres. We can here check uh, for the specs as we have declared before, and we can check also for the tags section. So we can see that these are the tags we have already defined and declared in our Terraform repo. Now back to the code, to the workflows. All what we have left is the drift detection workflow, which is already scheduled to be run, as we say, at 2 o'clock every night, so it won't be available to check now. But until now, here it is. This is what we have been through with our session. So, while we come to an end, what are the three things that I want you to take away? Let's say the first thing is to declare everything. If your infrastructure is not in code, it does not really exist. It's just a click waiting to be forgotten or changed by the wrong person or the wrong tool. So stay safe and declare everything. Second, we have the security by default. Trivy and Checkov can run on every pull request. Misconfigurations get caught in development and not in production and in post-incident review. And the third and final thing is observability. Full of this observability, cost estimates, security findings, and plan differentials on every pull request. Your reviewers have the full picture before they approve anything, and if you want to implement this at your organization, then Cloud Softway is your right choice. We provide, of course, an ultimate tier secure code DevSecOps framework built exactly for such purposes. So thank you for listening and see you next time.